Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and I'm joined this week by Jonah, who's one of our maths students.
Hey,
Jonah, you might recognise from the Oxford Online Maths Club last year. Jonah, what did you talk about last time?
I talked about partial differential equations.
Yeah, it was really good fun. There were Fourier series and things being added together and functions flying all over the place. But you don't need to have seen that episode to enjoy this one today, where we're going to be talking about, I think, something completely different. Is that right?
Yeah, massively different.
Massively different, because I guess people at university on a maths course learn about lots of different sorts of maths. James has got multiple interests and has agreed to come back on to talk about something completely different. So, Jenny, your title is Group Theory, Higgs Boson, and the Monster, which is quite a lot of things. There's quite a lot of exciting things in there. And I'm going to let you get started, but first I need to remind people watching that there is live chat available for this. If you're watching live on Thursday at 5, there's live chat in Slido where you can ask us questions. I'm keeping one eye on it to chat to people about the mathematics. Hello to Raphael, Molly, Ali, Brad, Alfie, and me. Almost did a shout out for myself and a couple of anonymous people. One of the things we like about Slido is that you can join it anonymously, or you can put in a name that's not your name. We've done a lot of mathematicians. I figured today, if you want to put an anonymous name in, maybe we should do musicians or something today instead of normally mathematicians. So I can already see a Ramanujan, who's not a musician, but more conventionally mathematician-y. Okay, and there's a website for the Maths Club as well. There's a link at the bottom of the screen and in the YouTube description if you want to watch sort of 30 previous episodes, including another one with Jonah. Further reading for every episode we do, including this one, is posted the day after the live stream with more links and information, stuff we didn't have time to get into the live stream. Brilliant. I can see that Jimi Hendrix has joined and said hello. So people, my microphone is switched on for this one, so that's good to know. Cool, right, okay. Jonah, I think over to you.
Oh, brilliant. Yeah, so today we're going to be talking about group theory, Higgs boson, and the monster. And I know they all sound like quite cool things. The main majority of this talk will be on group theory and like kind of what it is, a bit of an introduction to it. And obviously, if you're interested in it, there's plenty more in the further reading, and it's a really interesting area of maths that will come up time and time again if you go in to do maths further in the future. But let's get started. So group theory is kind of this mysterious mathematical idea that interlocks in loads of different regions of maths. But it's slightly hard to define. But the key idea is that it's got nice patterns, it's got nice applications. And as you can see, it kind of weirdly connects these three seemingly random diagrams. We'll meet the first two a bit in what we're about to do, and the third one is quite a complex idea, but a bit to do with like graphs and networks and stuff like that, which would be something you might do if you did group theory a bit more. But anyway, we'll get started with something a little bit nice, a little bit simple, something easy to digest. Squares. Squares are nice and easy and nice to talk about. So the first things first is, what do I mean by symmetry of a square? Well, a symmetry of a square is something we can do to a square to get it to land back on itself. And you may go, well, what does that mean? And so basically what we want to do is we want to take our square and we want to do something to it such that the corners land back on other corners. They don't have to be corners they were at before. For example, if corner 2 lands where corner 1 is now, that's completely fine. But we still want to maintain the square shape. We still want to make sure it's the same kind of orientation. So I thought I'd give you guys a bit of a chance to see if you can think of any symmetries of a square. I promise it's not a trick question. They're relatively basic ideas that you might have covered even back in primary school. But I thought I'd give you a second maybe in the chat, see if you can come up with any nice ideas. And just remember, yeah, the symmetries of a square is a nice, beautiful idea in math. Symmetries are so essential to everything, and we're going to be talking about them a lot today. But in fact, obviously, they're such like core ideas and such easy things to think about. Symmetries of a square. What is a square? What do we mean for something to be a square? What do we mean for something to? What can we do to a square to get it to land back on itself? I can't currently see the chat. In
In
case
chat, okay, I'll read out chat.
Yeah.
I told Johnny we'd ask chat things. Chat is being helpful already. There's a little bit of lag between us saying stuff, it getting broadcast, chat saying stuff, and it getting back into chat. I've remembered that I should have done a shout out for Flora and Christian, who are in chat helping moderate chat and replying to things as well. Flora and Christian are two more students. They're not on the screen, but they are here virtually as well, answering questions and talking about things in chat. Raphael says the chat doesn't seem to be updating on the stream. You're correct. There we go. I think I might have fixed it. The thing on the ticker at the bottom was broken. Chat, yes, lots of people in chat are saying reflections and rotations. I think we can be more specific than that, because there are lots of possible rotations, right? And not all of them are symmetries of a square. So
Yeah, that's exactly right. I like the chat's ideas. Yeah, exactly. Like, so if we rotated the square by, for example, 10 degrees, would that land this square back on itself? That might be something to think about. What ways? I mean, I like that the chat got rotations and reflections. That's absolutely brilliant. Exactly what we were looking for. But what exactly ways can we rotate our square so it lands back on itself? Right, have a little ideas, maybe some angles that we can think of.
I've noticed Alfie said something about reflections. I'm going to come back to reflections because I want to push on rotations as well. An anonymous person has said 90-degree rotations plural, and an anonymous person has also said rotation of 360 degrees. Should we talk about 90 degrees first?
Yeah, 90 degrees is definitely a brilliant idea. That's exactly correct, because we've got a nice square. If this was a rectangle, obviously 90 degrees wouldn't quite be precise, but a square, yeah, brilliant. 90 degrees is exact. I was wondering if anyone in the chat could perhaps get the exact number of unique rotations that we could do to a square. So after we've rotated it, the corners are in a unique position. So how many ways can we uniquely rotate the square such that it lands back on itself with the corners in a different position?
Yeah, so this how many question is a bit tricky because, well, I suppose somebody's already put in, sorry, my computer all the fans on my computer just fired up at once. Somebody's put multiples of 90 degrees. That's Alfie.
Yeah, exactly.
And there's a suggestion that there might be 3 different rotations from Ramanujan again and from Raphael. 3 possible rotations. What do you feel about that? I guess they mean 90 degrees, 180 degrees, and 270 degrees.
Yeah, that's. I mean, those are all 3 definitely unique rotations, and I mean, it's really good answers. And I love the multiple of 90 degrees because I think we're covering everything there. The one that the guys of you might have said 3 might have missed is the one that rotates the square to land back on itself, because we want a unique rotation, and the one we've got there is a unique rotation. The one that we can call it 0 degrees, we can call it 360 degrees, we can call it whatever we like, but we'll call it a unique rotation that lands the square back on itself. In group theory terms, we might call this an identity or something like that, but we won't overcomplicate things. We'll just say 0 degrees, 90 degrees, 180 degrees, 270 degrees. Absolutely brilliant. Yeah, so, give you guys a little chance to,
chat slightly because of the lag. That question has come up in chat as well, and I hope we've addressed that. That 0 degrees, we're going to count that, because if you rotate it by 0 degrees, then after your operation, all of the corners are in the places that they should be for a rotation.
Exactly.
Okay, and not 5. Right, so there's a question about anti-clockwise rotations. Do you want to say about anything if you rotate in the opposite direction? Is that?
Yeah. So, I mean, this may be something you can visualize quite nicely, but if you think about, like here I've said what happens to this square when we rotate it anti-clockwise by 90 degrees. If you just think in your head a little bit about what it means to rotate something I don't know if my orientation is the same on your screen, but anti-clockwise by 90 degrees is like that for me. And if I, for example, went all the way around like that, it's hard to move my arms like that. That's the exact same rotation, which would be an clockwise rotation by 270 degrees. So anti-clockwise, clockwise, I'm going to be using anti-clockwise a lot, but honestly, it doesn't really matter. So one rotation, one direction is a different rotation, other direction, obviously, apart from 0 and 180 degrees. So yeah, I was wondering if the chat can have a go at trying to work out what this square will look like after rotation by anti-clockwise 90 degrees. It's best to refer to the corners, because I call this square 1, 2, 3, 4, starting in the top left corner, like going round like that. So if you guys have any idea what this square is going to look like?
I'm going to read some more chat messages. So the question now is, can we specify what happens to the corners of the square if we rotate anti-clockwise by 90 degrees? In the practice session, I discovered that I don't know which way clocks go. John is also, so this is handy for chat, that you've given them a way to describe the square without having to draw little squares. If you can read off what the corners are doing after you've done this rotation. So people are saying 2, 3, 4, 1 to read, like, so you're reading clockwise from the top left, but you want them to do a rotation anti-clockwise. Yeah, there it is. Okay. I think we're all imagining.
Absolutely.
And 2, 3, 4, 1 is quite popular in chat. Okay. I think we're all imagining the same square, and you've got this way of describing it that they can do in chat, which I like.
I think this problem's going to come up a lot because we're going to be talking about some geometrical objects here, and they're often quite hard to describe in words. But we'll think about some nice ways we can talk about those.
Notation's great.
Getting back to yeah, I think it pretty much represents what I'm trying to demonstrate, the rotation anti-clockwise by 90 degrees, which is absolutely brilliant. So we've clarified the symmetries of a square. We've got rotations 0, 90, 180, 270. So we've got our 4 rotations there. And I remember the chat mentioning before, I was going to say what other symmetries of a square are there, but I remember James saying that chat's already suggested that reflections are also symmetries of a square. So how many axes of reflection does this square have? How many different ways can we reflect our square to get our corners into a unique position? Give you guys a chance to have a think about that one.
What are the symmetries? I think I'm trying to scroll through chat a little bit. I think someone had some descriptions earlier of the, was it Park? Yeah, how many others? So people are giving numbers as well for how many other symmetries there might be. There they go. Some people are saying 3 and 4, maybe 8 in total perhaps. Earlier people were saying maybe there might be 4 reflections. That seems to be a popular suggestion at the moment in chat. 4 different reflections. I think people have described them as well.
Oh, brilliant! That's one step further. 4 reflections is completely correct. I've drawn them there. I've got to be completely honest. I mean, I've been doing maths for quite a while now, and I still think I struggle to describe those reflections in words. I mean, something between like the axis of reflections going between corner 1 and 3, something like that. Not exactly an easy thing to describe, but yeah, absolutely brilliant. There are 4 axes of reflection, so 4 different lines we can reflect our square in to get a new square, or we get the corners in new position. And obviously, you guys get to have another go at this. We'll give it go reflection in the vertical axis, or that's the vertical one. See what. Once again, I get that referring to this, like telling me what the square you think is going to be the answer is hard. So corners is absolutely fine.
Trying to practice my descriptions with the camera reflection is quite annoying in course, isn't it? So I think it's that corner, then that corner, then that corner, then that corner. Oh, I did it. Yes, yeah. People are saying 2, 1, 4, 3 for this, for what will happen after you do this reflection. It's quite a bit of chat lag. I think the chat lag is different depending on where you're watching and what device you're watching on. But yeah, wow, a big wall of 2, 1, 4, 3, or possibly 2, 1, 3, 4 just came in through chat as well. Yeah. I think some people might be reading left to right.
Yeah.
Rather than, anyway, it's how you report back the square is tricky.
It's a bit difficult. I mean, the general convention within geometry is you normally read the corners off clockwise, but I mean, that's purely a convention. And obviously, if you're going to describe a shape, you need to explain your convention, because otherwise we've got a bit of a problem there. But yeah, I'll be reading them off clockwise. But yeah, 2, 1, 4, 3 is exactly correct. So let's have a little recap. Ooh. I've gone back a bit. Let's have a little recap. What exactly symmetries of a square do we have so far? So we have our rotations, we have our reflections. How many does that make in total? I know some of you said already that we've thought of 8 symmetries of a square, and that's completely right. We have our 4 rotations and our 4 reflections. And now the question we've got to think about now, and you might be thinking about a bit in chat, is, are there any more? And I think we can do a nice little bit of maths to try and work out the answer to this. So maybe have a little think of how many other ways we could look at a square and do some nice symmetries of it. Maybe there's something else we haven't thought of. I'm going to do a little bit of maybe combinatoric kind of number theory way to check, so we can see if there are going to be any more. But obviously, if you want to see if you can think of any more ways we can do something to our square, by all means have a go and post it in the chat. All right, so the first thing to think about when thinking of how many symmetries of our square there are is we want to think about where could each corner get sent to. So let's take corner 1, for example. That's our top left corner. Where could corner 1 get sent to? Well, as I'm sure you may realize, there are 4 different corners that corner 1 can get sent to because of all of our rotations that we've already covered. They all send corner 1 to a different corner. So there are 4 possibilities of where corner 1 can get sent to. Okay, so we've clarified that. Let's assume we choose which corner 1 goes to, right there. How many places are there in which corner 2 can go to? I'll give you guys a second to have a little think about this. So where could corner 2 go? Could it go to any of the other 3 corners? Could it only go to one of the corners? Could it go to 2 of the corners? How many corners could 2 possibly go to under some symmetry of the square? I'll give you guys a second to think about that.
So to catch up with chat, there's been some discussion about we counted the leave it alone symmetry, where you just leave all the corners the same. We counted that as one of our rotations, but not one of our reflections. It kind of feels like maybe some people were counting 5 reflections if you count the one where you don't do anything. And I've been trying to explain in chat how not doing anything feels to me more like a sort of rotation than a sort of reflection. And in chat I've said it feels more like a rotation to me because it doesn't turn the square upside down. And I'm not sure if I've got away with that. Suggestions in chat here. I've actually got all the numbers between 2 and 3 inclusive. I can't quite remember how you phrased the question. But was it how many possibilities are there for the next corner?
Yeah, how many possibilities are there for which corner 2 could go to?
Yeah, so this is, I guess, different from a permutations question. There's this style of A-level question where you might talk about permutations. There's 4 choices for the first thing and then 3 choices for the second. But for symmetries of a square, what's the answer?
Oh, well, symmetries of a square. Okay, well, we could think about this in a nice kind of geometrical way. Where can we send corner 2? Well, in fact, the answer is there are only 2 possibilities of where we can send the corner 2. And you might want to think about that. Why can we not send corner 2 to the one opposite corner 1? Well, originally, we had corner 1 and 2 connected, and that was a straight line connecting corner 1 and 2. So in order to send 2 to the corner opposite 1, we'd have to break that edge between 1 and 2. And now, okay, we need to break that edge between 1 and 2. Why is that not allowed? Well, we've been discussing this whole time kind of the symmetries of a square, things that we can do to a square, but we still want to keep the square. Like, for example, we can spin it around, we can reflect it, we can do all these things, but it's still the same square. If I'm breaking this square apart and putting it back together again in a different formation, we won't really consider that the same square. That's kind of been a bit cheating. It's like, for example, I could spin James about, I could put him on his head. It's still the same James, but if his arms were where his ears were or something like that, I wouldn't quite consider him to be quite the same James. I'm not sure, maybe you would, but I think there'd be something slightly different or slightly off there. And that's exactly how it is with the symmetries of our square. We can rotate, we can reflect, we can move things about, but we can't break things apart. So there are only 2 possibilities of where corner 2 could go. And so, for example, let's choose one of those corners. Let's say corner 2 gets sent to this corner right there. How many possibilities are there of where corners 3 and 4 can go? So where can corners 3 and 4 can go? Does it matter? Can corners 3 and 4 go either way? So 4 top left or 3 top left, does it matter? Or is there only one specific orientation? What do you guys think?
Okay, chat. I like that we had a difference of opinion. I'm going to skip over the bit where we tried to attach my arms to my ears. And I am on a spinny chair, so I can do arbitrary rotations.
Oh, brilliant. We'll get on to that in a second.
So the question now that you've just asked is, how many possibilities are there left? And chat, I think, is pretty unanimous that corner 3 has to be next to corner 2, so there's only one possibility for what the other corners are doing. This is, again, not quite like the permutation theory, where if you've got 2 things left, you can choose one of them. But here there's only one option, say chat.
Absolutely brilliant. Yeah, that's completely correct. By the exact same logic that we can't break the edge between 1 and 2, we can't break the edge between 2 and 3, or the edge between 1 and 4. So there is only one possibility. And so, okay, now let's do a little bit of fun maths to work that out. We said if we want to work out where corner 1 gets sent, there are 4 possibilities of where corner 1 can go. Once we've chosen that, that leaves 2 possibilities for corner 2, and then 1 possibility for 3 and 4. Now, if you maybe do a bit of probability at school, you know if we are choosing these events randomly, and without any bias, we can just multiply the number of those together to work out the total number of possibilities of symmetries of a square, the total number of ways we can send our corners to different places on our square using a symmetry. And so that gives us 4 times 2 times 1 times 1, which is 8. And we already have 8 so far, which means we found all of them. Brilliant. We're completely done there. Ah, lovely. So nice and easy. So brilliant. So that leaves us with 4 rotations. And I get that some of you were a bit iffy about the 0 degree being a rotation, but as I think what I've been said in the chat, stuff like that, reflections tend to be one that they send to something different and then could be undone by doing it again. I mean, that might be a very poor explanation. Maybe there'll be something better about that in the further reading as to why we might be considering the do nothing thing as a rotation rather than a reflection. But yeah, 4 rotations and 4 reflections, and that's absolutely brilliant. Okay, moving on. What connects all these symmetries? Like if I gave you a bunch of numbers and maybe real numbers or something, we can connect them by, for example, multiplying them together. That's a way that we can connect these numbers. How can we multiply together the symmetries of a square? Well, this is a bit of a complicated idea, so I might just go through it. But the main idea is something called composition. The idea is we can just do these one after another. So the same way I could say, oh, how am I going to multiply 5 and 2? I'll multiply them together. I'm going to get 10. How am I going to multiply rotation by 90 degrees and reflection in the vertical axis? I'll just do one, then do the other. And I'll consider that kind of my operation, connecting them. And an operation connecting all our elements of the symmetries is very important within group theory. So, brilliant. And our aim is to show that our group is going to be, we've covered all the symmetries of a square, even under composition, even like no matter, I can take whichever symmetry I like and I can do them in any order I like. And I want to show that we've actually covered them all. So I could do a rotation and a reflection and a reflection, it doesn't matter. It's going to be one of the symmetries we already have. So no matter how we compose them, we're just going to get another symmetry we've already created. And we've actually proved this already with our number counting proof before, but we're just going to check this right now just to make sure we're 100% certain on it. So first, can you guys give me an idea of what's going to happen to this square 1, 2, 3, 4 when I reflect it in its horizontal axis?
So we're going to do 2 symmetries, one after the other, and you say that. Okay, so chat's getting ready to tell me what happens after we do this. 2 symmetries, one after the other, and because we've already found all of the symmetries, this is going to turn out to be. Even after you do 2 of them, it doesn't get more complicated. It's just one of the 8 we've already found. People
exactly. We could do 4,000 of these, and it's going to turn out to be one of the ones we've already had. And we've actually proved this already.
Almost that this could have been a way of generating. You're about to combine 2 of these together. People are saying 4, 3, 2, 1 in chat, by the way, which feels like a countdown for more.
Yeah, 4, 3, 2, 1 is completely correct. And now, how about rotation by 180 degrees? I know I put anti-clockwise there, but as I'm sure you may realise, it doesn't actually matter because it's 180 degrees. But when you give that one a go.
I guess I was saying, this all feels like maybe. This could generate new and exciting symmetries of a square, more complicated compound symmetries. But I guess we've already found all of them, so there can't be any more complicated ones.
Exactly. We have 8 symmetries already, and we showed in the previous page that there are only 8 symmetries, and therefore we found them all. So now no matter what we do, we can't produce any new ones, and we're going to show that.
Consensus in chat so far from Tia and Molly and Alfie and Emily. And some anonymous people, and Grace is, and Jaden. I'm going to just shout out names for the rest of this stream. Consensus in chat so far from Alex and all the people I just said is, I think, 2143 for what's about to happen when you do this rotation.
Absolutely brilliant. Yeah, that's completely 100% correct. So we've applied 2 symmetries to this square 1, 2, 3, 4, and we've got to 2, 1, 4, 3. So do you think you guys can spot a symmetry that takes us directly from our first square to our third square? We skip out the middle step. Is there a rotation that takes, oh, is there a rotation or reflection, a symmetry, which takes us from 1, 2, 3, 4 to 2, 1, 4, 3?
Oh, okay, so they've got to type in chat now. I've just got to give them more time.
Yeah, no, that's completely fair. That's not.
I don't know how to get that.
Group theory is hard to talk about in a chat.
They're doing really well. Yeah, look, here's Emily and Grace and Romanajan and Galwa, Export Highway. People have spotted it. They think this might be reflection in the y-axis, in the vertical axis. Reflecting.
That's absolutely brilliant. Yeah, that's completely correct. And this is just one of many examples to show that we've already showed this, but we're just double checking that no matter how we combine any of our current symmetries of a square, we're only going to get one of the ones we already have. We've shown there are only 8 symmetries of a square, so no matter how we do symmetries, we're only going to produce ones we already have. So it doesn't matter how we combine them, you go ahead at home and try and think of the most complicated composition of symmetries in the world. I promise you, you're only going to be able to generate some on the list. We're going to move on to a slightly different section of the stuff we've been talking about. We talked about rotational symmetry before. We talked about the square. We can rotate it by 90 degrees or 180 degrees or whatever. But perhaps if we adjusted our square slightly and made it slightly irregular, we wouldn't be able to do this anymore. And this is something we're going to talk about now. And this is going to require a bit of visualization, and I have been making some very professional graphics at home, and I've been putting a lot of time and effort into these. So I just want a second to appreciate that. But okay, imagine you're in a desert. Imagine you're in a desert, you're standing right there in the center of a desert, completely looking around, and everything looks the same. No matter which direction you look, everything is the same. That is something we'd call rotational symmetry. No matter what direction you look, you're seeing the same thing. Now, imagine instead we did something to our desert that made it slightly less symmetrical, something that may be like a landmark. Suppose we start building out. Well, you know what? Like, I fancy a bit of a city in my desert. I'm going to start building a bit of construction, maybe turn a bit of a profit. Who knows? I'm going to build some houses and some buildings within my desert. I'm going to build them up, make them nice and pretty, all that kind of stuff. Now I know exactly which direction I look, because I look over there. Oh my God, that's the fountain I built. I know which direction I'm looking. Oh, that's my house. Like I know what that direction is too. We know exactly where we're looking. So there's no longer rotational symmetry, because we can tell which direction we're looking when we look there. It's not everything doesn't look the same. We can't rotate ourselves and have it still symmetric to what it was before. So what we call this is underlying symmetry. But the state, which is me building upon our desert, has meant there's no longer rotational symmetry. Now, we're going to relate this to a bit of quantum mechanics. So some of you may have heard of, I'm talking about 2 particles here, the electron and the neutrino. And many of you will have heard of the electron. It is what orbits the atom, and you probably talked about it in GCSE chemistry, maybe physics. It's a particle that many of you know. It's how current flows and stuff like that. Many of you may not know what the neutrino is. It's actually a particle that's sent out from the sun and doesn't really interact with anything. And loads of them pass through us all the time. And they do absolutely nothing. But so these particles are incredibly different. But actually, scientists have found that at the beginning of the universe, these 2 particles were symmetric. They were basically the same particle. They were very, very, very similar particles, and we could consider that some sort of symmetry between them. They had this symmetry that connected these 2 particles. And we wonder now, why are they so different now? Like, at the beginning of the universe, they had these really great symmetry that meant they were basically the same particle, and now they're so different and they do such different things. Well, this is where we get something called the Higgs field. The Higgs field is scientists' interpretation for what caused this underlying break in symmetry. Like when I built up my city in the desert, scientists believe that in the heat expansion of the universe, the Higgs field is what broke the symmetry between the electron and the neutrino. And the way it does this is usually something called the Higgs boson, which you may remember from the title of my talk. So this is where it comes up. We get the Higgs boson, which broke the symmetry between this electron and the neutrino to make them such different particles. And the way they did this, even though it's some random area of quantum mechanics, was using group theory. So I thought it'd be nice to talk about a little bit about some of the applications of group theory in some really cool areas of physics. And moving on, we can move on a bit. If anyone has any questions, they're more than welcome to ask. But otherwise, we'll move on.
Can we give them a second? Different. I really love this. So this idea of symmetry breaking, you can have evidence of symmetry breaking in the way that things aren't all the same. Sort of a bit like if the square that we were talking about was maybe crumpled slightly, or one of the corners was torn off, then that would change what symmetries we get out. It would be sort of identifiably different, and that there might be some processes that happened in the world that caused something like that. I suppose another way of saying it is something like you can detect things about the world based on the symmetries that you still have. So you can sort of detect, if you say I've got 8 symmetries, then maybe you're a square, to flip it around, and that you're not a sort of circle like my arbitrary rotation spinny chair with lots of rotational symmetry. If you've only got 8 symmetries, then some pretty serious breaking happened, and maybe you're now a square. Somebody's asked, what part of maths is this? And Flora, I forgot to mention Flora in chat has answered, it's physics, part of maths. There's a lot of maths in physics. There's quite a lot of physics in maths.
Yeah. Honestly, this is not the only time I might get a chance to mention some other applications of group theory within physics. Honestly, like the more in depth you go, the blurrier the boundaries are between different areas and different subjects. Honestly, like maths becomes physics, physics becomes maths, group theory becomes anything you could think of. It gets really weird.
Alfie in chat's asked, I don't know if you know the answer to this. You said something like they knew that the neutrino electron were once symmetrical in the past. Do you know how the evidence for that is? Or how did they know? I don't know at all.
It is quite a complex question that should probably go to someone who's a quantum physicist. But I can give a bit of an explanation of this.
Okay, maybe
it's because based on their rest masses and their spin, that they knew that they were symmetric at the beginning of the universe. So their rest masses and their spin was symmetric in a nice ratio formation, which I'm not exactly certain about. So it's probably worth putting in. I'll find something to put in the further reading or something like that. But yeah, it was to do with some very intrinsic states of the particles.
Okay, maybe they still have. Do they still have some similarities? I'm going to put it in the further
reading.
Yes,
they do. But yeah.
Okay.
Yeah.
Further reading. Right. Okay. More on group theory. Thank you, Alfie.
We good to move on?
Sure. Let's go. What have we got next?
Oh, okay. Well, we started with symmetries of a square, and I thought, well, why don't we have a little cool down? We can slow down a bit, move on to a triangle. Triangles are maybe a nicer shape than a square, maybe not nicer. We're only going to be talking about equilateral triangles, so we're not going to get some weird scalene triangle going on here. I'm not going to go through a whole process of deriving the symmetries of a triangle like I did with a square. I'm just wondering if you guys can think what the symmetries of a triangle are, of an equilateral triangle. What do you reckon they are? I mean, I'll give you a little hint. It's basically the same idea with what we did with the square, just with the triangles. So obviously there's going to be some slight changes, but it's very, very similar.
So symmetries of a triangle. I feel like someone in chat earlier had some. People in chat love algebra. I feel like someone had something with ends in earlier for what the answer would be if it wasn't a square but an n-sided shape. There's a multiplication argument that's come through. I'm going to give them. Tia's got an answer as well. And lines of symmetry. People are counting. There's a variety of approaches. People are trying to count the rotations and reflections separately, like you did at the start. Some people are thinking about how many combinations if you pick it up and then put the corners down to do a similar argument to what you did.
Those are both great arguments.
Yeah, but both of those approaches, either about thinking about putting the corners, picking it up and then choosing where to put corner 1 and then how to resolve the other corners after that, or the argument about counting the rotations and reflections separately, everyone seems to have got to 6 for how many symmetries there are for a triangle.
Nothing gets past this group. Yeah, no, 6 is completely correct. There are 3 rotations and 3 reflections, much like with the square where there are 4 rotations and 4 reflections, and maybe that will tell you something about how the sides of a shape correspond, or sides of a regular polygon correspond to the number of symmetries it has. Maybe that's something that also goes in the further reading. I mean, the connection is pretty clear, but the maths is very cool. But anyway, so we have 3 rotations here. Once again, we've got our 0-degree rotation. We've got our rotation by 120 and 240 degrees. And as you can see, they're going to land us back on the same triangle. And we've also got the reflection in the 3 axes of symmetry of our triangle. Absolutely brilliant. That's exactly correct. Those are our symmetries of a triangle. I'm now going to change course quite abruptly, and you'll see why I did so in a second, but here's a bit of an abrupt change in what we're doing. Imagine you have 3 objects, A, B, and C, in an order. So we have so they're in the order A, B, C. You've got them laid out in front of you. Nice little objects, A, B, and C. We can create a group of permutations, and this is, we're going to consider all the different ways we can rearrange these objects to get a new order. So we've talked about the symmetries of the shapes. We're going to now move on to how we can rearrange these objects to get a new order. So, for example, one of our ways we could rearrange these objects to get a new order is we could swap the first 2 objects. We could swap them around. We go from ABC to BAC, and that's a perfectly good permutation of our 3 objects. And don't think that we can only do this in one fluid motion. Another one of our permutations could be we could cycle them around. So we'll send ABC to CAB, for example. So it doesn't have to just be with one motion. It's just how can we take the objects A, B, and C and put them in a different order. So that's what a permutation is. That's how we permute our 3 objects. How many permutations do you reckon there are? So how many different ways do you reckon we can rearrange the 3 objects A, B, and C to get a unique order? I'll give you guys a second to think about that. Maybe worthwhile using a bit of maths similar to what we did earlier. Maybe not. Maybe you're going to go into some nice permutation argument. So have a go.
Sorry, I normally talk, but I was answering a question in chat.
Fair enough.
People in chat are saying, I like it when Abby and Tia and Joseph and Maddie's here, and some anonymous people. I do like. I can't remember if people are now using musicians' first names or their actual first names, but hey, it's quite nice for me to maybe pretend that these are people's first names. Maybe they are. People are saying 3 factorial or 6, or even Grace says 3 factorial equals 6. Both. People think there are 3 factorial permutations of these things.
Yeah, that's exactly correct. Yeah, we don't actually need to go about thinking of it as how many different ways we can rearrange these. We can just think of how many new orders there are possible. And exactly 3 factorial, there are 3 possibilities for the first one, 2 for the second, and 1 for the third. So that's exactly right. 3 factorial is the number of permutations of 3 objects. That's absolutely brilliant. Now, I'm going to ask you possibly one of the hardest questions of the day, or maybe one of the most interesting questions of the day. If we go back and consider the symmetries of our triangle right here, do you notice any similarities between these 2 groups? So I'll phrase that slightly differently. We've got our 3 objects A, B, and C, and we've thought about all the different ways we can rearrange these to make a new order of objects. How could that be similar to all the symmetries of the triangle? So all the ways we can reflect and rotate our triangle to get it into a unique position. I'll give you guys a second to have a think.
I guess. Somebody joined late and wants to know what was going on. Bit of group theory. We haven't actually defined a group. In case anybody's worried about that, I'm going to put it in the further reading. Don't stress. Yeah. We're getting by without having a definition of a group, and it's fine. There is a definition of a group. It's not super relevant right now. So there's some links. I want to read a couple of them out. I think. Keep typing if you're typing and I'm talking. So Erin says there are 3 objects ABC and there are 3 side / vertices in a triangle. I think they might have noticed that you've labelled them ABC as well. Tia says that the vertices of the triangle are like the objects in the group for your permutations, the objects in your permutations. X plus I always got a different word. They say that the permutations of the 3 vertices of the triangle what we're doing here. That's how they're linked. There's some link between the three things in your permutations and the permutations of the vertices. Emily says there are 3 objects. They'll be the same since vertex A will always be between B and C. I guess Emily is explaining that there isn't. It's always fine. Any permutation you do, A is always between B and C, whatever you do. Alfie says A can be in 3 places, B can be in 2 places, C can be in 1 place. So I guess that's a bit like doing the permutation as you build those permutations. I think I referred to it before of building up what you put down first and then what you put down second and third. It's kind of the same. That argument we did about counting all the symmetries for a shape is kind of similar to the argument you do when you're counting permutations. Like why is it 3 factorial? SV says some symmetry group triangles, possibly. Yeah, okay, something cyclic going on, possibly. Nobody said. I'll add in as well. Both of these groups, or whatever a group is, both these things have got 6 things in. Maybe that was too obvious an observation. It's also not a very helpful observation. But yeah, I really like these descriptions people are giving about the permutations of the letters A, B, and C are the same thing as symmetries of the triangle because that's how you permute the vertices.
Honestly, that is completely correct. I love this. It's really good because I wasn't sure whether people would spot that. But yeah, that's absolutely brilliant. It's completely correct. The same way that we can permute our 3 objects, we can permute our corners of a triangle in such a sense. Any order we put the corners of our triangle, A, B, and C, like someone in the chat completely correctly said, because A will always be between B and C, and same for the others, any combination of corners works for our triangle. And hence, we've got the symmetries of a triangle can correspond directly to a permutation of our 3 objects, A, B, and C. And similarly, the permutation of our 3 objects, A, B, and C, corresponds directly to the permutations of the corners of the triangle A, B, and C. And this is something we call an isomorphism. Now, it sounds like a big word, maybe, and obviously it is. And even mathematicians, it is a big word. But what we're saying is, in essence, these groups are considered to be isomorphic in the sense that they basically describe the same thing. If we consider our 3 objects to be the 3 corners of our triangle, we can see that there is a direct link between permuting these objects and performing a symmetry on our triangle. Those groups are pretty much the same. I'm going to give you a chance to have a go at this to see that. So here we have our triangle A, B, and C, and I've already done this one for you. I've reflected it in the vertical axis to get the triangle ACB. What permutation would be the equivalent of doing that on our objects A, B, and C, and what would be the outcome of that? I may have slightly given something away by referring to the triangle in such a way as I did, but it's quite hard to describe these triangles.
So this is reminding me that there is some sort of technical theory about, or people are putting things in chat. They don't agree yet. There is some technical theory about isomorphisms. It's a 5-syllable word. It's definitely a long word. There's some technical theory about isomorphisms that I guess we're not going to do. But how you actually pair up the technical specification of how you pair up the permutations to the symmetries. People in chat are either saying CAB or ACB. Or I think those are, or CBA. I've sort of forgotten what you asked. Is this how are we reading off the symmetry?
I'm reading off this symmetry. I'm reading off our triangle in my clockwise convention. So I'm reading off the corners of my first triangle as ABC. I'm not going to read off the corners of my second triangle because I don't want to give it away. And that's perhaps also quite a big hint.
Oh, I see. So people in chat who are saying Maddie and Tia and Erin and Anonymous who have said ACB for reading off your triangle and thinking about how that's a description of the position of the triangle, but it's also a permutation of the letters A, B, and C. And maybe that's how the matching up works.
Exactly, and that is completely correct. And what I really want to see is, because our group of symmetries and our group of permutations, I want to create a direct correspondence between them. So what would be the equivalent of reflection in the vertical axis? So like you said, you're completely correct. We've got to go from triangle ABC to triangle ACB by reflection in the vertical axis. What would be the equivalent of that in terms of a permutation from going from our objects A, B, and C in that order to our objects in the order A, C, and B? What would be the equivalence of that?
This. So people are talking
It's
about
not a trick question,
only
I
the
promise.
two corners at the bottom get interchanged, and you end up at ACB, which I think is because A lies. We're reflecting on a symmetric line. A is staying still. So it's at ACB. I think I might have got confused. Nobody's saying anything else. We've got ACB as our specification of the permutation. Swapping swapping B and C. Swapping those two.
I mean,
is that description?
Exactly
is that description we're looking for, or swapping there? Oh, I see.
I mean, yeah.
Okay.
Yeah, I get that there's not exactly a technical terminology for this, but yes,
swapping okay, so describing permutations, right? Okay, I see. Is this text on your arrow for describing the swap? Right, okay. Yeah, okay.
Oh, okay. So we say two groups are isomorphic if they can basically be thought of as the same thing. And like we've just shown, our group of symmetries of our triangle and our group of permutations of three objects are isomorphic. They can basically be thought of as the same thing. And just a little bit of added reading for you, a little bit of something you can think of further, and maybe go away and try and work on at home. Does the same thing exist between the symmetries of a square and a permutation of four objects? If we have some time at the end, maybe I'll discuss some of the ideas if people send them in chat, but there will definitely be something about this on the further reading. But yeah, this is a really interesting question. Like we talked about symmetries of a triangle and the permutation of three objects, describing basically the same thing. Does that same thing apply here? And I'm not going to spend any time on it because it's a bit more complicated a question, and because, partly just because there's an extra element and an extra member of our group, an extra corner, if you will, that's making things go up in a bit of numbers and stuff like that. I'm not going to spend time on it, but if you guys want to go away and have a go at seeing if you think there's a direct permutation of this, by all means,
chat's having a go. Chat's got a couple of approaches already. I'll put something in the further reading as well, though. Chat are pretty unanimous so far about whether these things are an isomorphism or not. Cool. Okay. So we've got this isomorphism idea for when two things that look like quite different things, like permutations and symmetries, which were, I think, two of the things on your first slide for these two different pictures you had, could actually be describing the same group. That the isomorphism could mean, well, that's just the same group in disguise, and you can describe permutations for three things and symmetries of a triangle with the same language of this. There is this group for what's happening to those three items. It's quite exciting because it means if you study group theory, then you can understand permutations and also understand symmetries of shapes at the same time, just by doing your group theory on that group that they have in common.
Exactly. So we can often take, if we have quite a group that might be quite hard to visualize, we could often take it and consider an isomorphic group, which is perhaps more easy to digest, a more palatable group that is easier to picture in our head. And we're going to go on to do a bit more about what these isomorphisms actually mean in the wider picture of group theory. So similarly to how you can factorize positive integers into prime factors, we can factorize big, complicated, grumpy looking groups into smaller, simple groups. So we can take out lots of different elements. We can break it apart into smaller, simple groups that are nice and easy to understand. And we can represent these groups in nice collections. And I just want to show you guys a diagram to help with my explanation of this, because I think this might be a nice way to represent it. We can represent these small, simple groups in a lovely little aesthetic table, which basically collects all groups together with similar properties. And we basically, there was a massive effort from hundreds and hundreds of mathematicians over a very long time to prove that this covered almost all groups, or all simple small groups, that this table covered pretty much everything. And the proof of this fact is actually over 100,000 pages long. In case you were thinking of having a little read through it, just like whilst you're in the bathroom or something, it's absolutely horrible. I don't think any mathematician has ever read through the whole thing. But yeah, we can represent these simple groups in a lovely table. Like I've compared it to the periodic table there, because it looks a bit similar. And the way we were talking about isomorphisms before, if two groups are isomorphic, they can basically be represented by the same square on our periodic table because they mean the same thing. our two groups are basically the same in every single sense of the way, apart from what they're talking about. Every single element of the group is the same. And so we only need to represent it as one group, as one square on our table. And so even though there might be loads of groups, if they're all isomorphic, if they're all representable as the same thing, we only need to take up one square on this table. And in fact, we can collect almost all nice, simple groups into a very aesthetic looking table, just like this. And bearing in mind that even if we have a really big, complicated group, we can break it down into small, simple groups. So much like we could have all the prime numbers, even though there are infinitely many of them, there are infinitely many of these, by the way, as well. We can break big, complicated groups down into nice, simple groups and put them in nice collections on our nice, pretty periodic table. And I think that's pretty interesting, pretty cool. Yeah.
I like that we know all of them in a way. It's a bit like these simple groups. We haven't said what simple means, but let's not worry about it. These simple groups are kind of the building blocks for other more complicated groups. They play a role that's quite a bit like prime numbers. In fact, that column down the right, I think the writing might be too small on the stream, but that column down the right is groups with a prime number of elements. They sort of match up with the primes. But there are these other groups as well. Groups are more interesting than the primes in some sense. There's more variety of them, but we know all of them. We know all of the families of groups that there are. So it's a little bit like if we factor knowing. It's a little bit like if we knew all of the prime numbers. A little bit, in an analogy sort of way. I shouldn't have said that. That was really complicated and involved a big analogy.
No, all prime numbers is a much harder thing. But yeah, no, this is clear. And you guys may remember that I said almost all groups fit into this table. Actually, we understand that we know every single possible finite group we have an understanding of, no matter how big it gets. We have a complete and perfect understanding of it. The only thing is that we've made a lovely table, really aesthetic table of groups, and we put them into lovely collections where they fit nicely and they have nice patterns. Now, I said almost all groups fit into this table because there are some groups that don't fit into this table. And in fact, it's quite a weird fact that there are 26 groups that do not fit into this table, and only 26 groups out of all finite groups. There are 26 kind of random groups which don't fit into our nice, pretty table. And these groups are called the Sporadic Groups. And you may remember from the beginning of this talk, my title was called the Group Theory, Higgs Boson, and the Monster. Well, the largest of these groups is called the Monster Group. And it is an absolutely ginormous group. When I say largest, I mean contains the most elements, like with our symmetries of a triangle containing 6 elements, our symmetries of a square containing 8 elements. I mean, you're more than welcome to have a guess at how many elements you think the monster group has. Also, please don't judge the graphic. I worked very, very hard on it, and a lot of blood, sweat, and tears went into that. So maybe have a guess in chat how big it is. It's absolutely huge.
Someone in chat says only 26 exceptions, not as bad as the periodic table. It's a bit like you know, whenever you try to tidy stuff up, you categorize everything, you sort them out into these little categories, and then you've always got this other category. And here it's got 26 elements, 26 groups in it. So it is absolutely enormous. Do you want to give them the number for how many elements are in this group?
Yeah. I mean, I'm sure some of you probably just guessed this straight off the top of your head, but it's got this many elements.
Of course it does.
I mean, yeah, I mean, sorry, I didn't want to make it too obvious. Yeah, that's how many elements our monster group has. And it's absolutely huge. This is of the order of 10 to the power of 53. So as you can imagine, it's a very, very big group. So it's quite weird how we've connected all of like infinitely many simple, nice groups into a lovely, pretty table. And there's 26 random outliers, which massively range in size, biggest of which being this weird size. There's nothing bigger. Like any group that's bigger than this number is automatically in the nice collection of groups. And there are only 25 other groups that are in this collection of groups. So that's pretty cool. I think it's worth mentioning some of the cool stuff about this monster group. So like we said that, oh, look, we had our symmetry group of a triangle to describe the symmetries of a triangle. It's not that that group can be called other things like the permutations of three objects, but it does also represent the symmetries of a triangle. Similarly, we've got the symmetries of a square. And I really wanted to draw you a lovely picture of what the monster group represents, because it does represent the symmetries of a shape. But I had slight difficulty because that shape is 196,883 dimensional. That's how big that shape is. It is absolutely huge. And so, as you can see, I was not able to draw that shape and draw the lines of symmetry on it. And if I had, it would have taken a very long time. And yeah, it's not a particularly nice shape, but it is a really cool fact that we could actually represent this group as a symmetry of a shape. And I mean, I've heard many people discuss what they think is a nice way to visualize this shape. It's perhaps the best idea not to try and visualize this shape because it's 196,000 dimensional, but maybe like a snowflake that is perhaps is one way, a very, very irregular hundred of thousands of dimensional snowflake. If that's something you can just think of off the top of your head, something that just might happen. Yeah, so a bit weird, but yeah,
there's a
very cool.
really nice. I think you mentioned it in the practice. There's a really nice number file video interviewing John Conway talking about the monster group and symmetries of shapes. I'll put a link to it in the further reading notes as well. John Conway is one of the people, influential mathematicians who worked on this to find this group. Somebody else, why is it called the monster group? I guess just because it's really big, right?
Yeah, because it's an absolute monster of a group. I mean, you can look at the number of elements. One of the people who discovered it said it was like looking into the face of God. It's such a big group, and it's actually really beautiful. I mean, you'd think that this group is so big, so random, that it has absolutely no applications whatsoever. But actually, a random group in the middle of nowhere, in such a random area of group theory, has loads of applications. It's actually a really important part of number theory. And you may have heard of the monster moonshine conjecture. You might not have, but you might just have heard of it because it's a funny name. But the monster moonshine conjecture is a conjecture which relates this monster group to a really cool area of number theory. Not only that, this monster group has applications in string theory. So, like I said earlier, where the lines between maths and physics blur, this random group has really important connections to string theory. Really, really random.
I love that this links to Vicky's session last week on number theory a little bit. I mean, not in a very direct way, which was just number theory is huge as a topic. But it also links back to Platonic solids from 2 weeks ago, where we talked about shapes and the different rotations that you could do on those shapes a little bit. Someone in chat ages ago asked about the symmetries of a cube, which I might talk about in the further reading as well. Grace has got a book recommendation in chat where Grace read about this, The Universe Speaks in Numbers, and somebody with a username Gawar would like to know whether this was discovered by computer, like with the four-colour map theorem. I think it was not discovered by computer. I think it was discovered by thinking very hard.
It was definitely discovered by thinking very hard. I mean, I don't know much about this. I mean, there are only a couple hundred mathematicians in the entire world that specialise in this kind of area of maths because it's so obscure. I mean, it's really cool, but it's very obscure. And we actually know loads about this group because loads of people have just dedicated their entire mathematical career to discovering or to understanding this group, even though it was only discovered like 50, 60 years ago. And it's absolutely incredible. And actually, I think the way they discovered it was basically just looking at all the ways they could combine simple finite groups like the ones we were talking about in our table earlier and seeing kind of where the things that didn't fit in happened. As you can see, this group ends with a lot of zeros, and that's actually not a coincidence. If you read a bit into it, you'll see why it ends with so many zeros, why it's got a factor of 100 million. The billion, I think. I can't really.
Lots of twos and fives in its factorization. Somebody's pointed out that this decimal expansion only has 1 3 in it. I think that's a coincidence, but I don't know. And it sort of scares me that I don't know.
No idea.
So brilliant. I love that chat's got research questions as well. I think Are we wrapping up in a minute because it's almost 6 o'clock? I think it's been a really fun start on group theory where I think we've managed to avoid doing too much technical detail stuff. I'll put links to technical detail stuff about group theory in the further reading on the website. But I think we've done a good journey through isomorphisms and triangles and squares. Thank you very much, Jonah, for coming along and telling us about Higgs bosons and monsters and group theory in general.
Having me.
I'm going to do a quick bit of reading chat to check that I haven't missed anything. I think I'm going to hang out in chat after the stream's turned off. I'm going to switch to typing in the chat as well. People in chat are mostly saying thank you to Jonah. Jonah can't see the chat, but I'm reading it out. So Tia says thanks for the episode. Avakar Khan says thanks, really good, thanks. Somebody asks what is Galois theory, which I think not now, but
Yeah,
not
not
now
now.
for Galois theory. Right, thank you very much. Further reading is going to be posted at some point tomorrow on the Maths Club website. Link down there, and link in the YouTube description as well. maths.ox.acdk/r/club. And we'll see you next week, Thursday at 5, for another bit of live mathematics on the Oxford Online Math Club. But from me and Jonah, from Flora and Christian in the chat, goodbye, have a nice evening, stay safe, take care, and we'll see you next week. Bye.